Contact light. Okay, engine stop. APA at a descent. Tranquility Base here. The Eagle has landed.
In 1969, Apollo 11 put a man on the moon. But this did not come without repercussions. As the 70s rolled around and liberation movements filled the streets, NASA's financial freedom diminished. After the costly Gemini and Apollo programs, NASA needed one that was cheap, but that would still give them a way to transport crew and cargo into space in order to carry out future missions. NASA's Space Shuttle Program was a story of incredible highs and sickening lows. It sent 135 missions into space and took more than 350 humans into low Earth orbit. But today, it is widely considered a colossal failure. It aimed to be a cheap, reusable method of sending people and payload into space, but it ended up costing more than the disposable rockets with which it competed. After considering the loss of the lives of 40 astronauts during the program, it calls us to ask, was the Space Shuttle Program really a success? Or was it indeed a failure, like everyone else says? But before we talk about the shuttle itself, we need to talk about rockets themselves and how they work. Rockets, like a car, convert fuel into movement. But that's where the similarities end. Unlike a car, which can push against a road, a rocket is in the vacuum of space. Or at least it's going there, and can't push against anything. So how can a rocket work in space then? This is where a gentleman who lived a long time ago comes in very, very useful. You might have heard of him. His name is Sir Isaac Newton. Newton's third law of motion states that all forces between two objects exist in equal magnitude and opposite direction. Essentially, every action has an equal and opposite reaction. As a result, if you throw something behind you really, really fast, it will push you forward with an equal force. This is how rockets work. The high-velocity exhaust exiting the nozzle of a rocket engine propels it forward with an equal force. However, if you're designing the rocket, it's not this simple. Rockets are almost entirely fuel. In order to escape Earth's atmosphere and get into orbit, a significant amount of propellant needs to be burnt. The propellant mass fraction of any vehicle is defined as the portion of a vehicle's mass which does not reach the destination. For the space shuttle, the destination was in orbit. To put it into perspective, if we do the maths on the space shuttle, we can see that its propellant mass fraction was 0.8395. Almost 84% of the rocket is propellant. But why does this matter? If we're calculating the acceleration of a car, or its force, we'd simply use Newton's second law of motion, F equals ma. However, for a rocket, it's not that simple. As a rocket burns through its fuel, its mass changes significantly, from 2 million kilograms to just over 300 tons. So, if you try to use Newton's second law in its simple state of F equals ma, you're going to get a very inaccurate result. You need to use the rocket equation. In May 1903, a Russian high school teacher called Konstantin Tsiolkovsky published Exploration of Outer Space by means of rocket devices. Tsiolkovsky is known as the founding father of modern rocketry. The reason this paper was so important was because he not only correctly predicted how rockets would operate, what fuels they'd use, and explained that it was indeed feasible for humans to venture into space, given expected advancements in technology at the time. But Tsiolkovsky laid the foundations of the mathematics that would allow it to be possible. He laid out the rocket equation. While the derivation of the rocket equation is too complicated to explain in this short video, essentially, it allowed future rocket scientists to calculate how fast their rockets could get going. It accounted for changes in mass, fuel efficiency, everything. It was beautiful. And he did it all before the Wright brothers' first flight at Kitty Hawk. Now we know how rockets work. It's time to analyze the success of the Space Shuttle Program, how these principles and equations were put into practice, and how people took science and safety for granted at a time when they were needed most. The program officially commenced on January 5th, 1972, armed with the goal of being able to utilize reusable components and a flight plan whereby the space shuttle would re-enter the atmosphere and fly back to Earth. NASA began designs in 1968, and in 1975, designs were ready. NASA originally aimed for there to be a rocket launch every month, clearly a high benchmark. However, it soon became clear that this was unattainable, leading to some accusing NASA of developing go fever. As mentioned previously, the Space Shuttle Program had a considerably lower budget than previous programs, mostly due to NASA's aim to make the program reusable and cost-efficient. The Office of Management and Budget, in an effort to moderate NASA's plan for making a Cadillac of space shuttles, severely limited their budget and asserted that there was no possibility of budget increases during the succeeding 5 years. This restricted budget meant design trade-offs, swapping safety for cost benefits. For example, weight had been a big issue, and the weight of the orbiter would put a strain on the shuttle's propulsion system. So, 2 escape rockets on the orbiter were scrapped, leaving the astronauts locked in the launch vehicle after liftoff. And, in another effort to economize, NASA cut spending on safety testing and other development work for the shuttle components. NASA's troubles did not end there. Not only were cost estimates off in the beginning, but they rose in unpredictable ways. Inflation had its effect. The true cost of launching turned out to be 20 times greater than the original estimate. There was also a thrust shortfall that restricted the payload, so each launch would bring in less income than initially predicted. NASA's hope that businesses would pay them to bring satellites into space was crushed when the European Space Agency organized Arianespace, a commercial satellite launch consortium, which successfully began competing with NASA. NASA lost business, and yet again, the cost rose. Safety was barely a consideration anymore. As money ran short, tensions ran high. Soon, the consequences of NASA's apathetic attitude towards safety became horrifically evident.
We have main engine start, 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Engines beginning throttling down now. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
Challenger, go at throttle up. Challenger, go at throttle up.
Francis R. Scobie, Michael J. Smith, Ronald McNair, Ellison Onizuka, Judith Resnick, Gregory Jarvis, and Krista McAuliffe. All were lost in what became to be known as the Space Shuttle Challenger disaster. The Challenger mission STS-51L was originally scheduled for January 22, 1986. It was one of the most exciting missions to date of the program. Dubbed the Teacher in Space mission, hundreds of school children were excited to watch Krista McAuliffe, the payload specialist, teach elementary school children from space. Despite the mounting anticipation, there were already obstacles in the way. The previous Columbia launch had to be delayed, leading to the postponement of the Challenger mission 7 times over a 25-day period until the 28th of January. This meant NASA was already reluctant to delay the launch any further. But worse, at 1 p.m. on January 27th, NASA personnel at Cape Canaveral became concerned about the cold temperatures of the launch pad. Temperatures were predicted to be around -5 degrees centigrade in the early hours of the launch day. Engineers were hastily told to investigate any problems that this may cause. What was found was that the cold may affect the resilience of O-rings, used in the solid rocket boosters to create seals. But the O-rings had never been tested in temperatures as cold as the ones that were predicted for the 28th of January, so they couldn't know for sure. There were also ice on the launch pad, causing concerns that the acoustics at ignition would create debris that could ricochet, possibly hitting the orbiter. But again, with no clear evidence, they went ahead with the mission. At 11:38 the following morning, Challenger lifted off the Earth. As the shuttle ascended, one of the seals on a solid rocket booster opened enough to allow a plume of exhaust to leak out. Hot gases bathed the hull of the cold external tank full of liquid oxygen and hydrogen until the tank ruptured. Challenger was lost 73 seconds after takeoff as a fireball erupted and the shuttle disappeared into a huge cloud of smoke. Collectively, the country grieved. No one had expected such tragedy. And rightly, people were outraged and confused. Inquiries were opened into the failure of Challenger in an effort to find answers to the question everyone was asking. What had happened? The ensuing investigation, called the Rogers Commission Report, discovered that the cold did indeed affect O-ring resilience, as the engineers had correctly predicted. The O-rings were what held the sections of the side booster together. The cold caused the rings to harden to such an extent that they would not be able to seal the joints against the hot gases created at ignition, increasing the amount of erosions. If both the primary and secondary O-rings of a section failed, it would lead to hot exhaust gas shooting out the side of the rocket booster, which would lead to catastrophe. What was even scarier was that it was discovered that NASA engineers actually had known about the O-ring problems long in advance. On numerous flights before Challenger, especially those during cold temperatures, the primary O-ring had failed and allowed propellant to blow by. But the secondary O-ring had prevented the propellant from escaping the booster. After they first noticed this, they tested the O-rings and believed they understood what had happened. However, the engineers noticed it kept on happening. Rather than installing the program to redesign the joints, NASA waived the requirements governing O-ring safety, accepting the risk of this known anomaly. The disaster resulted in a 32-month hiatus of the Space Shuttle Program, and when it resumed, as a result of the grim medicine that had been forced down the throats of everyone in the world, NASA's Go Fever had long since disappeared. To finish, we need to remember that the story of the shuttle is not all tragedy and failure. On the 24th of April 1990, Space Shuttle Discovery launched the Hubble Space Telescope into orbit. One of the most important scientific instruments ever created, it has allowed for thousands of discoveries in its over 30-year tenure. Without the shuttle, this mission would not have been possible. The unique design of the orbiter, with its large payload bay, allowed Hubble to not only be deployed, but repaired multiple times throughout its lifespan. Furthermore, the shuttle was the workhorse that allowed for the creation and assembly of the International Space Station. Today, the ISS is one of the most important symbols of human endeavor, teamwork, and our passion for scientific discovery and exploration. Without the Space Shuttle, it is unlikely that these two spacecraft, alongside the hundreds of others that the program sent into space, would have ever happened, let alone be as successful as they were. To conclude, the legacy of the Space Shuttle is a tumultuous one, filled with tragedy, cost overruns, managerial failure, and scandals. However, the missions it sent up into the stars will forever be a beacon of what humanity is capable of, and continues to inspire countless humans, even a whole decade after it was cancelled. And let's not forget that while the Space Shuttle is a symbol of humanity's burning desires to reach the stars, it is also the most complicated flying machine ever to grace our skies.